Hello, assume a developer wrote this piece of code where she wants to use the base class from a third-party library, here from the package from another place, in her compute something method. She does that by using the respective application programming interface, short API, and particularly by first constructing the base object, then calling the doSomething method on it, and finally returning the result by calling the getResult method. However, she missed to check a certain condition, namely to call the hasCharacteristic method right before the doSomething method, which prevents that a malformed object is used during the computation of the doSomething method, which otherwise would produce an error. This is denoted in API misuse. API misuses are very prevalent in the software development area, and therefore software engineering research has put much effort into detecting those API misuses automatically. In alignment with these works, we wanted to use GraphDistance algorithms to compare API usages and subsequently detect API misuses by these comparisons. These are my colleagues Paul Blockhaus, Jacob Krüger, as well as my supervisor Frank Ortmeier, and me, Sebastian Nielebock. But first things first, what is API misuse detection about? So when we have a client code using an API, most techniques look at different code sites, like other code files in the project or other repositories, collect similar code samples using also those APIs, and conduct a kind of specification mining to obtain specifications describing how this API should be correctly used. These specifications can be state automata, dynamic invariants, usage patterns obtained by a frequent pattern mining approach based on method calls, sequences, abstract syntax trees, or control flow graphs, and so on. Then the client code is compared to the specification, and in case it violates those specifications, it is considered to be an API misuse. Otherwise, it's considered to be a correct usage. One recurring data structure in this domain is the so-called API usage graph, short AUG. It was originally developed by Sven Ammann and colleagues, and it is a statically obtained multigraph from the source code of a method describing the data and control flow information, but particularly tailored for the API usage. On the left-hand side, we can see the AUG for our initial example. I won't go into detail of all the elements, but what we can see is that we have certain node types, like these ellipses, which describe object instances labeled with the object type, rectangles describing method calls, and dashed edges describing control flow, and solid edges describing data flow. We used those AOGs in previous work to generate so-called correction rules. A correction rule describes, when we have an AOG describing an API misuse, how this AOG has to be transformed to become a fixed version. And we generated those rules automatically by using false and fixed versions of already known fixed misuses. And we obtained these two versions via repositories. A rule can look like this, where we have an AOG with a misuse part and the AOG of the fixed part. And the nodes of those AOGs are mapped with so-called transform edges, describing how those nodes have to be transformed. And in case we have to add some nodes, we have special epsilon nodes describing holes in the misuse part. And all nodes depicted here have to be changed due to this addition in this case, either by relabeling nodes or by adding or deleting nodes. Based on the AOG and the AOG correction rule, we now present our misuse detection techniques based on the distance computation. Here we use a distance function that takes two AOGs and computes a value between 0 and 1, where 0 denotes that the two AOGs are equal, and 1 denotes that the two AOGs are most dissimilar. Further, we assume that we have an AOG C representing a correct API usage and AOG M representing a misuse, and based on these usages, we denote a correction rule of the form AOG RM to AOG RC as applicable if those four conditions hold. And basically this says when we compare the correct part of the rule AOG RC to the correct AOG C, or vice versa, the misuse part of the rule, AOG-RM to AOG-M, then those distance values are always smaller than when we compare something that is a correct and a misuse, or a misuse and a correct AOG. And we can generalize that, so when we do not only have one correct and one misuse AOG, but multiple correct and misuses here in the form of the set C and M, then we can compute the average of the distance values and keep the conditions. And here we have done that for the first condition, and we can compute the condition for the other threes analogously. And then we can use those applicable rules to assess an arbitrary API usage graph AOGU, from which we do not know whether it is a misuse, by computing the distance to the misuse part and to the correct part. And if the misuse part is smaller than to the correct part, we denote the AOGU as a misuse. In our paper, we wanted to find the best distance function, and that best means regarding the effectiveness that it produces a high number of applicable rules, and the precision and recall during API misuse detection is actually higher than to comparable API misuse detectors. And we also estimated the efficiency, that means the time to compute the distance values. However, the results are not shown in the presentation, but are given in the paper. Now I'm going to shortly present the ideas of the used GraphDistance algorithms that we used from the related work. The exact computation can also be found in the paper. First, we have the graph edit distance. This is a matrix describing the cost of adding, deleting, and substituting nodes and edges. And since its computation is known to be NP-hard, we have two variants, first using the A-star algorithm, and second using the Hungarian algorithm. Then we used also the maximum common subgraph, and this, as the name says, computes the largest common subgraph between AOGs. And here we also used the Hungarian algorithm to obtain this value. Then we used an algorithm from the web domain called node-node similarity, and this is a link-based similarity matrix that uses an iterative multiplication of the respective adjacency matrices. And finally, we have a graph vectorization technique called axis vectors, which obtains features from the graph, namely nodes and subpath up to a certain length, and then counts the number of those features in this single graph and use those frequencies as entries for the vectors. And then we can compare, compute the distance between the vectors as the using normalized norms, here L1 norm and cosine similarity, as the distance value. Moreover, we also have another additional splitting technique where we split the AOG into multiple subgraphs depending on the used APIs, and then compute, then generate multiple vectors for each graph, compute also multiple distance values, and compute the average value as the final distance value. And these are the four variants we have here. In our experiments, we used two datasets. First, the MooBench dataset consisting of already fixed misuses, where we have the misuse and the fixed version. And here we used a subset of 96 of those entries. And the AU500 dataset, which is a manually validated dataset of API usages, whether they are misuses or correct usage. And here we used a subset of 493 of them. For the MooBench dataset, we generated all misuse AOGs and all correct AOGs as the sets M and C we have seen before, as well as the correction rules. And then we used the M and C sets to decide whether the rules are actually applicable. And here we also measured the time needed to compute the distance values. Then we used all applicable rules and generated the AUGs for all misuses and correct usage of the AU500 dataset and checked whether these represent a misuse based on our distance-based misuse detection condition. However, our results are sobering. First, most distance algorithms do not produce applicable rules, and those that produce applicable rules have actually a very low precision and recall. Here we only present the best values, and these are still lower than the values we have seen from from existing API misuse detectors. Therefore, we did a qualitative review of the distance computation and found some hypotheses that could improve the results. And two of them are first that reusing the rules internally, that means in project, may increase the precision and recall. And regarding the access vectors, we could improve the results by only using specific API information, not using frequencies but indicators as vectors, as well as further investigating, splitting, and comparing the subgraphs, which could further improve the results. And we found also additional hypotheses not mentioned here. We can conclude that simple distance algorithms are currently not sufficient. However, we found some hypotheses that could improve the results, and this will be also part of our further work. This closes my talk, and you can find our dataset and our replication package on Zenodo, as well as a preprint of our paper on ArcSci. Now I'm happy to take your questions.